Hi, everyone. My name is Adam. I work for an organization called Satalia. We use artificial intelligence, data science, machine learning, and optimization to solve efficiency problems in industry. So typically, these are operational problems. So we do vehicle routing for one of the largest grocers in the world, takes in 100,000 orders a day, and then assigns orders to vehicles and the sequence of deliveries of those orders. We do staff scheduling for one of the largest consultancy firms in the world. We do infrastructure planning for 3Mobile, which is essentially looking at the demand in any given area and then optimally placing signal boosters in order to maximize coverage whilst reducing demand. I'm going to talk about a couple of different things. First of all, though, I want to get everyone on the same page in terms of what AI actually is and what is data-driven decision-making. There's a huge amount of hype and speculation around data science, machine learning, and all of these different technologies, and I want everyone on the same page in terms of what these technologies actually are and what they're capable of. So, for a system to be truly data-driven, it has to have three components. The first component is data, getting data. And this is technologies like the Internet of Things, sensors, databases, data lakes, infrastructure, APIs, and so forth. Getting, processing, managing, structuring, making sense of data. The second phase is taking that data and putting it through a model of the world, to generate some predictions, to make some insights, or to recognize some patterns, okay? This is predictive analytics, yeah? Everyone gets excited about the term predictive analytics, and this is using technologies like machine learning or data science or natural language processing to make some predictions or generate some insights, okay? So a very basic model might be that the hotter it gets, the more ice creams you sell. Right? You get some data, you put it through the model, and the output might be, it's going to be 20 degrees tomorrow, you're going to sell 100 ice creams. Okay? The third stage of data-driven decision-making is a bit that everyone forgets about. It's the actual decision-making component of the system. If you have a model, and it's predicted that you're going to sell 100 ice creams tomorrow, so what? What are you going to do with those insights? What are you going to do with those predictions? Optimization would say that given you're going to sell 100 ice creams, you need to hire this many people, spend this much on marketing, manufacture this many ice creams. It's the resource allocation component of the system. And what's happening in most industries today is you have these predictive systems, these predictive models that are making predictions or generating insights, and you have humans. You have humans or people that are left to make the resource allocation decisions, okay? How do we allocate our resources to leverage those insights or make decisions? And I'd argue that humans are really, really bad at solving these types of resource allocation problems. Let me give you an example. Imagine you have 15 Pokemon, okay? And your challenge is to arrange these Pokemon in a certain way so that you satisfy a number of rules, okay? The males have to go next to the females, the red ones have to go next to the blue ones, and so forth. How many different ways of arranging these Pokemon do you think there are? And I know it's slightly abstract, but this could be people with different types of skills. It could be infrastructure with different types of characteristics. How many ways? Anyone have a guess? Over 1 trillion. With 15 things, there's over 1 trillion ways you can arrange it. With 500 Pokemon, there are more ways that you can arrange them than atoms in the universe. Okay, so industry at the moment, you have these predictive systems. Everyone's excited about predictive analytics. It's generating insights, making predictions, but humans are the ones to solve these types of problems. These are exponentially hard problems. No human on Earth are going to solve these types of problems, okay? And this could be anything. This could be marketing budget, how do we allocate our people? Every organization, every industry has resource allocation problems that probably are being solved suboptimally. Okay? We solve these types of problems for organizations. So we don't do anything with Pokemon, but we have a client that instead of having 500 employees, has 200,000. Okay? And the challenge is how do you allocate those members of staff to relevant consultancy projects based on demand, based on skills, based on experiences, location, preferences, holiday, and so forth. These are incredibly hard problems, and that final piece of that decision-making stack is often left out of lots of systems. However, we'd argue that isn't true artificial intelligence, okay? So a system is data-driven when it has a component that gets data, puts it through a model of the world, and leverages those insights, leverages those predictions to make good and efficient resource allocation decisions. For a system to be intelligent, Our favorite definition of intelligence is goal-directed adaptive behavior. Yeah? It has to have a goal to sell more stuff or reduce costs. It has to be able to behave, to allocate resources in some way. But crucially, it has to be able to adapt. Okay? Most systems today in production are not adapting on their own. You put a system into a production environment, it does what it does. You then take it out of that production environment. You give it to some engineers, some data scientists, some machine learning experts. They then update the model, adapt it, make it more sophisticated. Then they put it back into production. That process of adaptation is done by people, and it takes about 3 to 6 months to do so. Until that process of adaptation is done by the model itself, in production, in real time, we'd argue it isn't true artificial intelligence. And the reason why it's very hard to build that system that's adaptive in production is because we cannot predict how these systems will adapt. We cannot predict how they will behave. A couple of years ago, Microsoft released a bot. Not sure if anyone saw it. It was called Tay. They released that bot on Twitter. They exposed it to all of the data on Twitter, and it became a racist, fascist bot. Okay, you cannot predict how these systems will adapt until we cannot put them into production environment and allow them to make decisions on our behalf. Okay, so just on a little bit of the work that we do as an organization, we did some work for Three, okay, and we did 2 things here. Three had a big problem in that their customers were complaining of bad signal, poor signal in very busy areas. So we did 2 things. Firstly, we took all of the data that they generate on their network, the usage data. We combined that with public data about weather, about seasonality, about events, and so forth, to build a predictive model that predicted the demand of any given area at any given time of day or time of year or whatever. Again, that's machine learning. You're making a prediction. So what? You have to do something with those insights, with that prediction. We used optimization algorithms to optimize the placement of signal boosters around the country to maximize signal for maximize coverage for the maximum number of people whilst reducing the cost of infrastructure. And we did so by about 18%. Similarly, we've done it for the entire fiber network of Scotland. Okay, it's a similar challenge. How do you minimize the amount of physical fiber infrastructure that you use whilst serving the maximum number of people? And again, there are constraints. There are rules. You can't just dig up houses or dig up roads. You have to do it in a safe and regulatory way. And these are the types of problems that we solve. So in a world of smart cities, what does technology look like? What kinds of technology do you need in order to build a smart city? And I'd say you need all 3 of those components. So let's imagine you have a city whereby there's self-driving, autonomous, ownerless cars. So no one owns any cars. You get a car, it takes you to work, it drops you off, it picks someone else up. Okay, what do you need for that system to be productive? You need Internet of Things to understand where that car is or where people are. You need machine learning to identify demand in any given area that can be calculated with historical demand, real-time demand, weather, seasonality, events, natural disasters. You need to be able to predict demand. Again, finally, making a prediction is not good enough. You need to use optimization algorithms to then optimize the allocation of resources. And this is where optimization comes in. Given the prediction of demand, where do you place vehicles in order to serve that demand in the best possible way? What's the optimal route for those vehicles to take? What's the optimal sequence of drop-offs that it can make? Okay, so for a city to be truly smart, it cannot just be making predictions. It has to have a full stack of capabilities in all of these 3 technologies. And obviously, the adaptive component will come as we learn to build systems that can adapt in ways that we can predict. Thank you very much for listening.